4.6 is on Newton's method. It is used for approximating zeros or roots of an equation or a function. So let's first suppose that we want to find the root r of f, or a root. I mean, there obviously could be multiple zeros of a function. All right, so here's the idea. Let me draw a picture actually first. So if you have a function, and it could have multiple roots. I'm going to erase this first drawing, but you could have multiple roots like this, but we're going to focus just on kind of one area, like right there. Okay, so let's just do that. Let me erase that. So draw in some sort of curve. Let's suppose it goes something like this. And then right here, obviously, is the root. Okay, so, and suppose we don't know what that is. So we're looking for r, and how do you have a method to find that? And so you got to realize these methods to find roots were developed for different reasons. One, to actually approximate roots quickly without the use of computers or calculators, when this was originally done. But it also gives theory to convergence concepts and things like that for future use. And you can figure out how maybe a sequence converges and other things like that. So these lead to other things for the future. So what you do is you choose, so this is my function f here. And so we want to choose, we're going to say x sub 1, a first value. That's called a seed value. Sufficiently close to r. Now that's kind of hard to define, but I'll show you some examples later what we mean. So let me zoom in a little bit here. So you want to choose a value, say, let's just make it right about, well, we're kind of exaggerating a little bit. So let's make it here. Okay, so you're going to choose x sub 1 to be here. We don't know r, and we, theoretically, we'll never actually know it exactly. We will look at an example where you're approximating a square root. And that's exact anyway. So it's square root of, say, 5, but you want to get the decimal approximation. So this is kind of how you do it. So then what you do, okay, so we choose, let's go back to my procedure. Choose x sub 1, the seed value, sufficiently close to r. Okay, then p of x1 f of x sub 1 is a point on the graph. So is a point on the graph. All right, so let's zoom in here. So this point on the graph would be this. So you go up to the graph. Okay, so this point here is the value or point x1 f of x1. And so from that, we will be able to find the tangent line. So we're going to look at the tangent line to that. Let's call it here, like that. And we'll be able to figure out the equation of that tangent line. But notice how that tangent line comes down and then intersects the graph, or the x-axis, closer to r. Okay, and you can see, if you picked a point over here, the same thing would occur. Like you do a tangent line and it's going to hit here. So this is how this value here, we're going to solve for. This value is going to be a x-intercept. I'll derive this in a second. That'll be x2, and you'll be able to solve for that. Okay, so let's continue the derivation here. All right, so using y minus y1 equal to m times x minus x1, we can derive the tangent line to f at P. We can derive the equation of the tangent line to f at P. So our first line, we're going to call that line L1. So L1 is going to be y minus f of x1, that's the y value up there, equal to the slope we know as the derivative, f prime of x1 times x minus x1. So that's the equation for any point of the line. That's all of these points. So we want the x-intercept. We want x to be 0, and x. We want to figure out x2. Where did that hit? That means your y value is 0. Okay, so if the x-intercept is x2, 0, which is the point in question, we substitute and solve, and you get 0 minus f of x1 equal to f prime of x1 times x2 minus x1. So really all I'm doing is saying I want to find the value that is the x-intercept. So that value is, let's just call it that. And you can see that it would possibly hit here. So now what we're going to do is solve this equation for x2. Okay, so do that. Solve for x2. I won't go through all those little details. So the other thing we got to do is say this. So assuming f prime of x1 does not equal 0, we may solve for x2. Okay, so we're going to solve for your x2 value. And you get, so just picture, it's pretty easy. You are going to distribute, and you're going to add the x1, and then you're going to divide by the f prime. It doesn't have to be that order, but that's what you end up getting. So just confirm you get this. So x2 is equal to x1 minus f of x1 all over f prime of x1. All right, so then what we do, so picture that being like a value like, like 1.6 instead of 1 or something. Now we're going to use this x2 as a closer value, what we call the next seed value, and do the same process. Okay, so where were they? Okay, so we use x2 as the next approximation. Okay, so it's the next approximation for the root r. And you apply the same process. So then you get x3 then is equal to x2 minus f of x2 all over f prime of x2. And that's true provided, of course, f prime of x2 does not equal 0. So you can't divide by 0 there. So then you'd apply this in general. You get a recursive relationship, we call it. So apply this in general. And you get Newton's method. You get of how to do it. So we'll define it recursively. So this is what we call Newton's method. Pretty much going to give you like the formula and some assumptions now to go through this. So Newton's method. First, let f be differentiable. Period. So it's differentiable, and suppose R is a real root of f. So you see how just graphically it won't work for an imaginary root, right? It has to actually hit the x-axis. So if you had x squared plus 1 equals 0, then you're going to have two imaginary. So it doesn't work for those. You can't get that. So you have to kind of know where to look is the idea. All right, so then let f be differentiable, and suppose R is a real root of f. Okay, then if x sub n is an approximation to R, then the next approximation would be x sub n plus 1 is given by x sub n plus 1 equal to, well, then it's the same process, right? I mean, look at what you're getting. This is the next one, and then you have n, f of n over its derivative n. So it's that's what you would expect. So you get x sub n minus f of x sub n over f prime of x sub n. Okay, and that's, of course, provided x prime of x sub n does not equal 0. Okay, so that's the method. Let's look at now what we'll say. These are what I call, these are cases Newton's method will fail. Okay, so let me draw on a graph, so just so you can see what's going on here. So let's do this graph. Try that again. Okay. So if you have some graph, let's see, you have to do it kind of like this, and then, okay, something like that. Then there's a few cases we got to be careful of. Let's do a different color here. One, so here's your roots. So there's a root there and a root here, kind of close together. So if on something like this, you choose your seed value too far away, like say right about here, then your tangent line, so it goes to here. Now, you're kind of closer, but now your tangent line puts you really far away. Like that. So there's your tangent line. Well, this point over here is too far. So this is your x1. Then this ends up being your x2. And then you go back up to the graph. And then that may or may not, well, actually that one does work kind of, but that'll put you farther away. Okay, so what you don't want is your f prime of x1 to be close to 0. Okay, so we don't want that. So I don't want to say that. So we don't want this. So the same thing like here, if you have your, so here's your root, right? And then you pick your x1 like here, and it's not close enough. You go up to the graph and you do your tangent line. Well, your tangent line puts you way down there. That's kind of exaggeration, I guess, on that one, but so let's just move it a little bit. So it's too far away. So in that case, let me just move it over. So if here's your choice of your x1 here, then your x2 is way down here. And then the graph maybe does something like this, comes down and then goes up. And then all of a sudden you're like way over here. You just keep getting farther away. So you got to be careful that you're close enough and it works. It's not really well-defined concept other than, is it giving you, sorry about the thing there, I'm trying to get it to bubble there. All right. Is it getting you closer and closer to a value? So you'll know if it starts converging or not, is the idea. Okay. Let's do an example. Okay, so let's apply Newton's method to do this example. So use, and I would specifically say this, so use Newton's method to approximate, and this is just an example, say square root 7 to 5 decimal places. So what you do on something like this is you know that a root of that is going to be x squared minus 7. So we're going to let f of x equal to x squared minus 7. We know that f is continuous and differentiable on the reals. We can do its derivative pretty quickly here. We can get f prime of x is just 2x, because we're going to need that in the formula. All right, so then one question might be is, how do we know there's a root? So we want to find c such that f of c is equal to 0. Okay, so the question is, how do we know? Okay, and so I'm not talking about just setting it equals 0 and solving. I mean, you can just, say x squared minus 7 equals 0. X squared is equal to 7. So x is equal to plus or minus root 7. So that's what we're trying to solve. But between what two values? So what is the seed value? that's really the question. What value do you choose? And obviously, you can just plug in a calculator, but that's not how we want to think of it right now. So let's just kind of take a look what happens. So by the intermediate value theorem, which I do want you to look up, intermediate value theorem, there exists a C in the open interval from 2 to 3 such that f of C is equal to 0. Since if you do f of 2, so this is really what you would do first, actually. This is your first step. F of 2 is equal to 2 squared minus 7 is equal to negative 3. So you get a negative value. And then you get f of 3. I'm just picking values, like 2 squared is 4, 3 squared is 9. What squared gives you 7, basically? So f of 3 is 3 squared minus 7, which is equal to 2. So therefore, by the intermediate value theorem, you have a negative and a positive. It must intersect in between. Okay, and we're looking at basically a parabola, and you're going to get negative and positive, and you put a value here and here. There has to be a root in between. So that's what we're looking at. Actually, let me draw a better graph than that, at least for the first explanation. So if you were to graph this thing roughly, you know it's down 7. So 2, 4, 6, 8. So right, say here. And then we know the roots are basically the square root of 7 and the negative square root of 7. If you just counted off values, we know you get, it's going to look, well, let's graph it. Looks like this and like this, right? We know it's a parabola, opens up like that. So if you test, what did I put in? 2. So put in 2 and 3, right? So you get 1. So this is the value down here. What was it, negative? Put in 2 and you get negative 3. You put in 3 and you get 2. So there must exist a root in between. So there has to be a root right there, because that's what we're looking for. So what you can do as a rule of thumb, if you get something like that that seems reasonable, just pick halfway in between. So choose x1 equal to 2.5. So it's halfway between, where was it? 2 and 3. So 2 and 3. And I don't want you to worry about the seed value, because I'll probably tell you, because it works out better anyway if everybody has the same seed value. So, so you can figure out positive, negative if you're looking for a root, and you choose halfway in between. So that's what we're going to do here. All right, so then you have your x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So what we have then is our first value you put in then is going to be the 2.5. Okay, so you're going to substitute in the 2.5 right there, get your next value and plug it back in. So let's do it down here. So your x sub 2 is going to be your 2.5 minus f of 2.5 all over f prime of 2.5. Okay, so do that evaluation. Okay, so you can pause and kind of get ahead of me here. So 2.5 minus, and then you're substituting into your function value, which is x squared minus 7. So then this is 2.5 squared minus 7, that's in parentheses, over 2 times 2.5, because f prime is just 2x. And you evaluate that. I'll try that on your own, and you get 2.65 and then a bunch of zeros. So that's your next seed value. That's your x sub 3. Or I mean that's x sub 2, but that's what you use in that formula. So it's 2.65 minus, let's just break it up like this now this time. And then just substitute in. So it's 2.65 squared minus 7 over 2 times 2.65 equal to, and you get 2.64575. And so that's actually, what did it say? 5 decimal. So 1, 2, 3, 4, 5. That's 5. So you want to do it one more time to see if it's close. Okay, and once you get that, you get that repeat once, then you have 5 decimal places. This, what we say in this type of formula is that it converges really fast. So Newton's method has a really, really fast convergence if it does converge. Okay, and then, oops. So it's 2.64575 squared minus 7 over 2 times, and then you put that in again, 2.64575. Calculate that, and you'll get 2.64575. And then that repeated. So once that repeats that once like that, then you're good. I didn't do the whole calculation, but you get other digits here and here. But once you've repeated to 5 decimal places, you're done. Okay, so make a little note here. Stop at 2 consecutive write that better. Stop at 2 consecutive. I did it again. Values of x sub n that are the same. Okay, so that it's the same, and it's the number of decimal places you want. So this converged to 5 decimal places basically in only 2 iterations. If you go farther away from it, it may take longer, but this one went really quick. So remember, if your f prime right here is real close to 0, then this is going to be a weird number. So like if you pick a value like here, it's going to just shoot you way off like that. So you don't want to do that. You want to get closer and closer to the number. So that's the square root. That's how square root type things were approximated before computers and stuff. So square root of 7 is approximately 2.64575, and you can verify that if you want. But remember, we're not doing that just for fun. Like these concepts of convergence and repeated values approaching infinity equaling exact values and things like that is a theory for a lot of things in the future of math. So this is just the beginning of that. So what I usually say, there's other types of questions on there, but this one it will be used to find an approximation of a root, like a cube root or a square root or something like that, where you do this process. So this is the type of thing I would ask on like example we just did.